Hello, and welcome to today's session on correlation, where we are continuing our earlier discussion on this topic. Today we'll be describing these three topics. Specifically, we'll be talking about how to show your correlations graphically by using scatter plots, and we'll talk about some of the clicks that you might make inside of a software package called SPSS. Then we'll also look at the clicks that you might do to generate those correlations inside of SPSS. And in this case, we'll be talking about a particular kind of correlation called the Pearson correlation, which we had described in an earlier video. You might recall that this is something that had been developed by Carl Pearson. Then we'll go on to an alternate kind of correlation called Spearmans Rho, sometimes called Spearmans R. Before we get too far into this, though, please make sure that, as always, you have the PowerPoint lecture notes printed and in front of you so that you can take notes on what is clear and also on what is not so clear as we go through the video. So let's begin by talking about this graphical idea of scatter plots in SPSS for our conversation today. And as you'll see, the idea of scatter plots really doesn't depend on any particular software package, but we'll use SPSS to motivate today's discussion. To set the stage for this, why don't we think about a naturally occurring phenomena, depression. Depression is something that is of interest to psychologists. It's a pervasive problem for humans and presumably for non-human animals as well. And as scientists and psychologists, psychologists being a particular type of scientist, we're very interested in making precise measures about this naturally occurring phenomena of depression. And we're going to be looking at two scales. One is the Hamilton Rating Scale for Depression, and throughout the next few slides you'll see HRSD, and we'll also look at a related kind of a scale, related in the sense that it's a measure of the same construct, depression. This is the Beck Depression Inventory, or the BDI scale. What I have here, it might not be obvious on the video, would be the wiki links for each of these, just in case you'd like to read a little bit about the background and the history and the regular usage of these two different scales for depression, but we don't have to do that right now. We're also going to open up inside of SPSS a file called Feeling Good, and this will be a sample file that contains measures on each of these scales at two different times, time 1 and time 2. So we'll have to remind ourselves as we're going through that we sometimes are talking about this scale. It'll be followed by a 1 if we're making that measurement using this scale at time 1, and we might have the Beck Depression Inventory, or BDI, at time 1 or at time 2, depending on when that measure had been taken. Okay? So we have two different measurement scales taken at two different times. That will be our data set. That data set is called Feeling Good. Okay. So we'll ask you to sign on to SPSS and open up the Feeling Good file. Just as a reminder, inside of SPSS, the data files always end in .save. And we'll use that .save data file to produce a scatter plot, focusing just on the pictorial information. We'll get into how to compute the R statistic in just a little bit, but we'll do the pictorial information first. And what we'll do is create a scatter plot in which we attempt to predict HRSD1, that's the Hamilton Rating Scale for Depression, at time 1. We'll put that on our y-axis, which we call our ordinate. And then on our x-axis, we'll have the Beck Depression Inventory scores taken at time 1 also. This will be on the abscissa, or the x-axis. Just a little bit of terminology. We've introduced this terminology one time before. Whenever we're creating scatter plots and we're looking at correlational data, we typically describe the x-axis variable as the predictor variable, and the y-axis variable as the criterion variable. So here's predictor, here's the criterion. In this case, HRSD1, that's the Hamilton Rating Scale for Depression at time 1. That's going to be our criterion variable. And then on the abscissa, we'll have our predictor variable, the Beck Depression Inventory scores at time 1. Okay. Now, once we're inside of SPSS and we have our Feeling Good file open, here's the series of clicks that we're going to make. We're going to go first to the Graphs menu, and then we'll look at a submenu called Legacy Dialogues. These have been carried over from prior versions of SPSS, and we'll take the Scatter Plot, Scatter Dot option that you see here, and there are different varieties of those. We're going to be looking at something called the Simple Scatter. We might choose later in the semester to try some variations on that. For the moment, we'll keep it simple, and we'll go with a simple scatter, and we'll define which variables we're going to be looking at on the x and y axes. We don't even have to specify which is which. We'll just plug those in, and we can click on OK. Again, here are the two variables of interest. Okay? All right. And then what we'll do is we'll see the output, and we'll do this in class, and I will ask you these two questions. First, just based on the visual information, can you state a plausible R value for what we will generate in class? And just as a reminder, we'll think about the Pearson R statistic first, because these variables will be defined continuously using a ratio or interval scale. And we'll remind you that the Pearson R statistic can range from -1 through 0 to +1. That's the range of possible scores that we could have here. So looking at the scatter plot that we generate in SPSS, what would a plausible value be? And maybe you can tell me why that would be plausible. And then similarly, we'll ask you to identify two implausible R values for the same scatter plot. Okay? And the reason why we do that is we want you to develop intuitions about how the R statistic is working and what kinds of data are linearly distributed and which are not so linear. Okay? We'll be talking about nonlinear formations and nonlinear trends later in the semester. For this discussion, though, we'll be looking at linear patterns in the data. That is to say, patterns that are well described by a straight line, maybe sloped upward, maybe sloped downward, but a straight line nonetheless. Okay? So what we'll try to do is repeat this one more time. We'll use the same criterion variable. That's the Hamilton rating scale for depression at time 1. That'll remain on our ordinate or y-axis. But now we'll swap out the old variable on the x-axis and swap in a new variable. And that'll be the Hamilton rating scale for depression, but now time 2. Okay, so we can ask about the relationship between these two, okay, across time. So same scale, but now at a later time. That'll go on the x-axis, which we call the abscissa. And we'll add that to our other scatter plot, and then we'll have two scatter plots. And just by visual inspection, we might try to see which of these two is the better predictor. And we can do this more formally by looking at the R statistic itself, but that might be a good way to develop some intuitions. First, by putting out the scatter plots and seeing about the linear relationship between these two variables shown across each of our two scatter plots. Okay, let's just set the stage a little bit and harken back to something that we learned earlier in the semester. You'll recall that the scientific method has 4 goals: description, prediction, understanding, and when we say understanding, we're talking about causal relations, and then creating change. These are the 4 goals that we're going to be returning to time and time again. We've already talked quite a bit this semester about description. We've talked about descriptive statistics. You might recall that we said that when we are using descriptive statistics, we typically indicate some sort of central tendency, mode, median, or mean, and also we offer an indication of dispersion. And some common examples there include such things as the range, the difference between the maximum and minimum scores, and also the standard deviation, the average extent to which a score departs from a mean. Okay? Now we can bump it up a notch and try to get up to prediction. And we'll remind ourselves that correlational stats, like the Pearson R, which was developed by Carl Pearson, allow us to predict. Now, interestingly, Carl Pearson's formula, as you might remember, is based very heavily on means. And that's important because of something else that we said earlier this semester. And that is, we can make a distinction between parametric tests and non-parametric tests. A parametric test is going to be one that's based on a mean, and Carl Pearson's formula is based on a mean. For example, we can remind ourselves that the Pearson formula was based on the sums of squares. Sums of squares are based on square deviations from the mean, so we have to compute a mean first. Carl Pearson's formula is also based on something that we learned called the sums of products. Well, the products are actually the products of deviates from the mean. So we're very dependent in Carl Pearson's formula on the mean, and that can be a good thing under certain circumstances. There are other kinds of tests, though, that are not based on means, and we call these non-parametric tests. One that we'll introduce a little bit later on is called Spearmans Rho, but we won't get too far ahead of ourselves. We can use correlational statistics to predict, and that's an important goal in the scientific method. It's one of our 4 goals. The stronger the absolute value of the R statistic, the better the prediction. So a predictor that has an R statistic of -1 is just as good as one that has a predictor of +1. Okay? We don't really care about the sign. In fact, we don't care at all about the sign. The absolute value is what's going to be driving the extent to which we can predict our criterion variable, which is shown on our y-axis, or our ordinate, to use our parlance. Okay? So that's a little bit of background about what we might do graphically with our scatter plot inside of SPSS, for example. Now let's see how we might use SPSS to go to the next step. That is, we want to formally compute the Pearson correlation. And we'll see later on we can look at other kinds of correlations as well. Pearson happens to be a parametric test. We'll take a look at that one first. It's probably the most frequently used correlational statistic. Okay, so what we'll do is we'll compute the R statistic relating HRSD1. Again, that was the Hamilton rating scale for depression at time 1. That's on our y-axis. And we'll correlate that with our Beck depression inventory scale at time 1 on our x-axis or on our abscissa. This is our predictor variable. So this is the scatter plot that we generated first a moment ago. We took a look at it and we tried to informally come up with some plausible and implausible values. Hopefully you have some intuitions about why the numbers that you generated would be plausible or implausible. Now we'll actually get the computer to give us the very specific Pearson correlation statistic. To do that inside of SPSS, we would use the following steps. Okay, to get that R statistic, and this again is the Pearson, we're going to go to the Analyze menu, and we're going to go to Correlate. This is a correlation, so that's intuitive. Here's a less intuitive word for some of you, bivariate. I'll come back to that in a moment. After we click on the bivariate option, we'll move in the x and the y variables into the variables box, and we'll select the Pearson option for a scale measure, and we'll go from there, and we'll get some value between -1 and +1. Okay? And generally speaking, we're interested in the strength of that relationship, but also the direction. Okay, so we'll be looking at those two things. Okay, so before we go further, let's come back and talk a little bit about a word that might be intuitive to some of you, but less so to others of you. So for those of you who are familiar with the prefix bi, as in bicycle, for example, bi means two, and you can see that the root word of variate might be variable. So in a bivariate correlation, we're looking at two variables. It might be, for example, the Hamilton scale measures at time 1 and the Beck depression measures at time 1. Okay, we're looking at those two variables. One is on the x-axis, and one is on the y-axis. Not all correlations are bivariate. If you take the next course up in our sequence, you'll experiment with something called multiple regression, where we might try to predict one variable on the y-axis from a host of variables on the x-axis. Here, to get the ball rolling this semester, we're talking about bivariate correlation and also bivariate regression, as you'll see. And that means that we have two variables at a time, and that's a good way to get started. Okay? All right. Then what we'll do is we'll return to the second of the two scatter plots that we had computed a little while ago. And we'll look once again on the y-axis for the Hamilton rating scale for depression at time 1. But now we'll get the correlation with that and the Hamilton rating scale for depression at time 2. So same scale at a later time, just as we had done a moment ago for our scatter plots. And we'll see what kind of correlation we get there. We could look at those two R values and figure out which of the two is the better predictor, reminding ourselves that prediction is one of the Fab Four, one of the 4 goals of the scientific method. Okay, so now we've learned how we might use a software package to help get a graphical depiction of these correlations, and also a very precise quantitative, indeed parametric measure of these correlations, the Pearson R statistic. Okay, so what I'd like you to do now is stop the video and jot down what has been clear to this point and what has been less clear, and we'll resume in just a moment. Okay, welcome back. Now what we're going to do is talk about another correlational statistic called Spearmans Rho, sometimes Spearmans R, and we'll see in what ways there are similarities to the Pearson R and in what ways there are differences. Okay, so to get the ball rolling for this in the classroom, we'll use SPSS one more time, and we'll go to a different data set just to give you a little bit of variety. We'll go to the General Social Survey data set that we have available to us out on our shared drive, and we'll look at 3 other variables that might be of interest to you. We'll look at one variable shown here in red called respondents' income, and this will become our criterion variable. This is what we're going to try to predict. And we're going to use one predictor at a time. The first predictor that we're going to use is the highest year of school completed, so that will be our educational variable. And then we'll use a different kind of sociological variable called age when first married. And one at a time, we'll use each of these predictors to try to learn something about the criterion, specifically what is correlated with the criterion, which is the respondent income. And in this particular case, we're going to use the Spearman R to make that prediction, also called the Spearmans Rho. Just a little bit of background on this. What you might notice when we go into the GSS file is that the creators of that file have operationally defined these variables, respondent income, highest year of school completed, and age when first married, on an ordinal scale. It wouldn't have to be that way. You could operationally define these lots of different ways. These particular researchers happen to have defined these particular variables on an ordinal or ranked scale. That's going to be very important for reasons that will become obvious in just a moment. What we're going to do is see, according to the Spearmans R, which variable, highest year of school completed or age when first married, is the better predictor of respondent income, and why we say that, why we come to the conclusion that we do. Okay? All right, so let's see if we can understand a little bit about these statistics. So Spearmans Rho is similar in some ways to Pearson's R because both range from -1 to +1. In both cases, a R value of 0, either in the Spearman case or the Pearson case, would indicate that you have no correlation whatsoever. Okay? All right. Different correlational statistics, though, are used for different measurement scales, and this is where we begin to see how these two differ from each other. They're both correlational. They both go from -1 to +1. We can look at values that are measured on a nominal scale, and we might use something called the phi statistic. We might use something called Kendall's tau to look for correlations or associations between variables that are measured nominally. You might remember the synonym that we had for nominal scales as being categorical scales. Okay? There are other kinds of measures that we could use here as well. One is called the chi-square. I'll say a little bit more about that in just a moment. But to keep our momentum going within this slide, we'll talk a little bit about the next most precise scale, and that would be the ordinal scale. It has greater precision, provides greater information than does the nominal or categorical scale. And when we do have ordinal data, which is to say rank order data, then the Spearmans R, or Spearmans Rho, would be the appropriate statistic. Again, we use these two interchangeably, Spearmans R or Spearmans Rho. So a moment ago, we said that we had these variables operationally defined on this rank ordered or ordinal scale, and so it would be appropriate to use the Spearmans Rho for this particular measure. Okay, and then finally we have interval or ratio data. This would be the most refined and most precise type of scale that we could use. And here we could use the Pearson's R because now we can take such things as means. Means are kind of like ratios when you think about it. We have the sum of all the scores divided by the number of items that we have in that list of scores. And so that's a ratio of sorts. A ratio scale would be appropriate. And when we can use that kind of parametric investigation, we typically prefer to take advantage of the precision that is afforded by that level of scale, and we would then use a Pearson's. So we have different kinds of measures that are completely contingent on how you've operationally defined your variables. Okay? So hopefully you can see a little bit about the connection or some sort of relationship between what we said earlier about research methods and how these relate now to different kinds of statistics. Okay, so this semester we will not be computing, at least manually, the phi nor the Kendall tau statistic that would be appropriate for nominal scales. Later this semester we will learn a statistic called the chi-square. In fact, we'll learn a couple of different varieties of chi-square statistics for evaluating associations among categorical or nominal variables. Just to harken back to an earlier example on this to put a little bit of context for the chi-square that we'll come to in a few lectures, you might remember that we looked at book carrying behavior in an observational study, and we wondered whether there might be some sort of gender association going on with book carrying behavior. Book carrying we defined as being side carry. Sometimes people carry their books over here as they're walking. Sometimes there's front carry. As we talked about, the people will hold their books toward their torso. And there's sometimes people will carry their books in a very different manner. Neither front carry nor side carry. We can call that other. So we have three different categories of book carrying behavior. And we can have maybe two different levels of our gender variable, male and female. Not everybody thinks of gender as being so dichotomous, but some folks do conceptualize it that way. We might operationalize it as male and female, and then three different levels of our book carrying behavior. And then we could say is we can use our chi-square to find some kind of association for these nominal variables. Okay? But more on chi-square in a few videos, a few lectures from now. Okay, let's get back to Spearmans Rho. Okay? And like the Pearson correlation coefficient R, the Spearman's rank order correlation, Rho, as it's sometimes called, indicates the strength of the relationship between two variables. So as we said before, that's how they're similar. The Spearman's Rho does range from -1 to +1, as we mentioned. That's how they're similar. So both correlational, both operating in the same range. The difference is that, unlike the Pearson, which is used for interval or ratio data, the Spearman is used for ordinal scales. So as we said a few minutes back, that if we're looking at respondent income as one particular example, we can choose to operationally define that in a way that is ratio. But in this particular case, in the general social survey, it was defined as being ordinal. So we might then opt for the Spearman. Okay, so there are 3 cases in which we would actually distinguish the Spearman from the Pearson and actually prefer the Spearman over the Pearson, which I think is interesting. When both variables are on ordinal scales, then we would favor the Spearman. Similarly, we would favor the Spearman when one variable is ordinal and the other is interval or ratio. So when we have a mixed bag. And then finally, when the statistical assumptions underlying the Pearson are not met. Whenever we have a Pearson R statistic, we're talking about a parametric test. Often that's preferred because it provides greater precision. On the other hand, these come with a set of assumptions, and we'll unpack the 3 different assumptions associated with that in a few minutes. We'll come back to those assumptions, and we will revisit that time and time again this semester. But what I'd like to do now over the next 3 slides is just say a little bit more about each of these 3 conditions for which we would prefer the Spearman over the Pearson. Okay, so let's see if we can get into this first idea about ordinal variables. So again, we prefer Spearman over Pearson when both variables are on ordinal scales. Okay, and to say just a little bit more about that, here's the formula that you don't have to memorize for the Spearman's Rho. In fact, I'm not even sure I'm going to have you compute this manually. But what I would like you to appreciate is that if you take a look at the formula, it does not require any mean or any average, okay? Unlike the Pearson formula. And for this reason, it's said to be non-parametric. Okay? So the Spearman formula is computationally simpler than the Pearson because we don't have to do sums of squares, which are based on means. We don't have to do sums of products, which are based on means. It's really quite straightforward. The D that you see here is for rank differences. We have rank ordered data here. We're dealing typically with ordinal scales. Okay, so it's quite a bit simpler computationally if you were doing this manually. And when both variables are on ordinal scales, it's a no-brainer. We're going to be using the Spearman. Let's go on to a slightly more complicated case. This will be condition 2, when again we would opt for the Spearman over the Pearson. Okay? Now let's say that we have this mixed bag case, this hybrid case, where one variable is on an ordinal scale. Okay, so far so good. But the other variable is on some kind of, inside of SPSS, a scale measure or scale level of measurement, either interval or ratio. Okay, so what do we do if we have one variable in each of those camps? Okay, so here's typically the idea. The scale variable, that's the one that has greater precision, it's measured at the interval level or the ratio level, needs to be converted to ranks. And then Spearman's Rho is computed on the 2 sets of ranks. So we start out with one set of ranks, and then we initially had one variable in our bivariate analysis. That was interval ratio. We can convert that downward into a more rudimentary or cruder scale. In this case, it would go from interval ratio down to an ordinal scale. A note about that I hope will be intuitive to you, but we'll see if we can unpack it in this way. Scores can be converted downward in sophistication from scale down to ordinal, or from ordinal down to nominal. Okay? Scores cannot be converted upward in sophistication. So for example, if I have something that's measured on a ratio scale, I can choose to unpack that in such a way that I can say, well, this one would have a better rank than that one, and this one would have a better rank than that one. Okay? But if I only have things ordinally measured, I really don't know what the interval is between them. So I can't go upward in sophistication, upward in precision, but I can always go downward. So in this case where we have a mixed bag, one variable is ordinally defined, one is defined on an interval or ratio scale, which is called, somewhat unfortunately, scale inside of SPSS. I can take advantage of that level of precision, and I can rank order those those particular scores, and away I go with my Spearmans Rho. Okay, let's go on to our third condition. And this brings us back to the distinction between the Pearson, which is parametric, and there's an alliteration there that you might want to take advantage of, versus the Spearman, which is not parametric. Okay? So when the assumptions for the Pearson R fail, then we would revert to using the Spearman Rho. Okay? Now, what are these assumptions? I'll introduce them here, and then we will return to these assumptions throughout the semester. Okay. The first assumption for the Pearsons are, okay, so this is the Pearson, and we have to make all three of these assumptions and demonstrate that they're satisfied for the Pearson to work. Scores on each variable are normally distributed. Okay. So as always, we have some variable on the x-axis, some variable on the y-axis, and each of those variables would have to be normally distributed, that is, distributed in a roughly bell-shaped manner. If we have a strong skew in one of those, then we probably should not be using the Pearson. And there are ways of using advanced statistics to tell us about the magnitude of the skew that we might have, the departure from this perfectly symmetric bell-shaped curve. Okay? To the extent that we have a departure from this normal Gaussian distributed data set, then we probably should get away from the Pearson and resort to Spearman's. Spearman's is more of a catch-all R. We can use it in many different circumstances. Okay? So that's our first of three assumptions. Let's go to our second assumption. If we're going to use a Pearson's R, then the second assumption must be that the variances are approximately equal for the variables. And here, I think it would be best if I draw this. So I'm going to escape out of this and just put a picture or two on the board, because I think this might help us. So as we've been talking about correlation, we know that we're looking at the relationship between our x variable and our y variable. And we want to think about now this notion of equal variance. So let's see how variable a set of scores might be by way of picture. And what we'll do is we'll draw first a simple histogram. And you might remember that histograms typically have a variable of interest here on the x-axis, and we have frequency on this axis. Okay, so that's our frequency. And we might have, for example, the x variable, whatever that might happen to be. Okay? And that'll go from low scores on this side to higher scores on this side. Okay? So one of the ideas, as we mentioned a moment ago, was that we hope to have a bell-shaped distribution of scores on the x variable. And we also want to have them, the two variables show similar variances. So let's see if we can draw that. First, we'll say that we get some good news, and we get more or less a bell-shaped curve for our x variable. Most of the scores here are in the center. We have relatively fewer scores that are at the high extreme, relatively fewer scores at the low extreme. I probably haven't drawn a perfect Gaussian here for the moment, but that's okay. This is at least roughly normal or Gaussian or bell-shaped. Okay? That's our x variable. Of course, in bivariate regression, we have to look at two variables. So we'll now look at the frequency, as always. For our y variable, which we'll call y var. And again, we have higher scores up here, and we have lower scores down this way. And it might be the case that we get roughly the same kind of variability on this axis, or this y variable. So you might see that this is a little bit narrower than that, but they're about the same. Okay? And so it might be the case that a formal test of the width of these bell-shaped curves, which is an indication of their dispersion, as indicated most specifically by their standard deviation, probably these two are close enough to each other, even though this one's a little bit narrower than that one is. Okay? There's a test called the Levene's test for equal variance that we'll be seeing later this semester, but that's probably close enough. What I'd like to do, just by way of demonstration, is show you a wildly different variance. Suppose x were distributed just like this, with standard deviations as shown here, but let's pretend that y had very, very little variability. Shown here in red, I have a very small variance and a very small standard deviation in this particular case. So this and this would be very different from each other. And the Levene statistic for equal variance would probably tell us that these two are sufficiently different that the assumption of equal variance has been violated, and we probably should use some other statistic than a Pearson statistic, which relies very heavily on equal variance. Okay? So we'll bring this back up, and we'll move on to our third assumption. Bring this down. Our third assumption is one called the independence assumption. that each score is independent of every other score. This might be the assumption that's most difficult to develop some intuitions about, but I'll offer you this just to get the ball rolling. You can imagine that we might be health psychologists, and we're interested in weight reduction programs. So what we would do is measure weight at time 1, have people go through our program, and then measure weight at time 2. Pretty straightforward kind of regimen that you can imagine, and we can ask about the scores on these two different measures, time 1 and time 2, weight in each of those cases. Okay? What we might say, though, is that if somebody like me weighs approximately 130 pounds, it's probably the case that at time 2, yes, my weight might be different, but you wouldn't imagine that it would be wildly different. Okay? Let me give you a little further elaboration on that. Let's say there's somebody else in our weight loss program who's starting out at 260 pounds. Okay? And then at time 2, we measure them again. They're probably not going to be exactly 260, but they're probably going to be closer to 260 than I would be. Okay? That is to say that if I'm starting out at 130, and somebody else in my weight loss group is starting out at 260, you might imagine that at time 2, I'm still going to weigh less than that person will at time 2. In other words, our time 1 scores are in some ways associated with our time 2 scores. They're not independent of each other. Okay? What we need to have is a formal independence between the two sets of scores, such that any given score is not dependent on any other score. Here's one more example. Okay? It might be the case that we're looking at running times, and we're sports psychologists, we're interested in who's running the fastest on our track team. Well, you can imagine that what we could do is time people and measure things on a ratio scale, because time can be measured on a ratio scale, but then we might rank order folks. And what we might say is that if a particular person is occupying a particular rank, that might preclude somebody else from occupying that same rank. So if you come in 5 seconds faster than me, then I can't have the same rank as you. Okay? Once that rank is taken, you've excluded me from that rank. So the score that I have is somewhat dependent on the scores that other people are forming. And because there's a dependence of my score on the other scores, then the scores are not independent of each other. Okay? So hopefully this gives you some idea about a violation of score independence, and we'll come back to this third assumption that underlies the Pearson statistic a few different times. We'll revisit these with some other examples, but that might give you some feeling for how it is that we talk about the assumptions that underlie the Pearson. Okay? Okay. So now what we're going to do is return to the issue of converting scores from an interval or ratio scale downward in sophistication to an ordinal scale, and we'll assume that we have 10 pairs of scores. Okay, and we'll see how we make this kind of conversion. Assume also that we want to convert all scores to an ordinal scale. And the reason for doing this is we're trying to get a Spearmans Rho going, and we want to have 2 sets of rank-ordered data. Okay? It might also be the case that you and I are interested in replicating an earlier study, and the earlier study had used the Spearmans Rho. So we'll take a look at how we might go ahead and do that. In this hypothetical, we'll assume we're looking at something that might be very important to you, the numbers of hours that you spend studying, and your exam scores. And we might first have these data in some kind of ratio scale, because it is in fact the case that you can have absolutely none of this quantity, number of hours studied, and absolutely none of exam scores. Also, the interval is satisfied. The distance between 40 and 60 is similar to the distance between 60 and 80. There's a step of 20 there, and 20 means the same thing. So we have ratio data here. Okay? And what we want to do is take this left-hand panel and convert it into some kind of rank. So same scores, but now we begin rank ordering these scores. Okay? How do we do that? Well, the first thing we might do is take a look for the lowest number, and that happens to be 2, so that's going to get a rank of 1. Then we can go to the second and the third number, and we might look for the second and third lowest number. Here's a 5, here's a 5. Now, interestingly, we have 2 5s there, so there's a tie, and this is typically what we do for a tie. The second and third numbers are equal to each other, so what we might do is take the mean of those 2 ranks, not the mean of these 2 values, but rather the mean of the 2 ranks, which would be 2.5, and we assign a rank of 2.5 to each of the scores that were 5 on this list of number of hours studying. Okay? And we can go on down the line and look for the next lowest value. It might be that 9 is the next lowest value. We could peruse this and try to figure out what the next lowest score might be. Okay. All right, finally, we can compute Spearmans Rho on the ranks, okay, once we have the ranks for each of our variables, and this would turn out to be 0.973 if we were to do this inside of SPSS, for example. Okay? And we're not going to manually compute Spearmans Rho this semester, but we can have the computer do that for us, and we might see that we have a strong negative value or that we have a strong positive value, but now we have a non-parametric computation of the statistic, in this case on ordinal scales. Okay, so what I'd like you to do now, as always, is think about what we've talked through in this video and see if you can make a note of what was particularly clear. That's an important step in your mastering the material. Please don't underestimate that. And also, of course, write down what was not so clear, and I look forward to taking your responses in class. See you in class.